All right, everyone. So we're looking at topic 2.7. It starts on page 41. And we have this big guide here. And what I've decided is that this guide that's on page 41 and 42, that's what we're going to be doing during class time. We're going to be filling these things out together. But before we do that, I want you to be familiar with what each of these things are. So first one is domains or steric numbers. Okay? So if we have a Lewis dot structure and there is one terminally bonded atom and then a lone pair. Okay? So bonded atoms is we have our central atom and then we have one that's bonded to it. So if this is the center, then that's our bonded atom. This would be one bonded atom. And then there are 0 lone pairs, so we don't have any lone pairs. Okay? So the Lewis dot structure would be something where there's a center and then it's bonded to a single atom. One that you might be familiar with is like a hydrogen bonded to a hydrogen. One of them is the central, and then we have a bonded atom to that. That is a steric number or a domain of 1. These things together, the bonded atoms, not counting the center, okay, so the terminally bonded atoms, the ones bonded to the outside surrounding the center, plus the amount of lone pairs, those together are electron domains. And when we add them together, we get something called the steric number. So for this one, we have 2 bonded atoms and 0 lone pairs. So an example would be carbon dioxide. Like, you know how we have carbon in the middle and then it's double bonded to 2 oxygens there. And it doesn't matter that it's double bonded. It's bonded to 2 atoms off of the center. So they could be single, double, or triple bonds, but this would still be a steric number of 2. No lone pairs on the center, 2 bonded atoms off of the center. Okay? So I'm going to keep going now. And instead of giving actual examples, we're going to do this structure where A is going to be in the center. A is always going to be my center one, and then I'll be bonded to X. Those will be the bonded atoms. But keep in mind that this could be a single, a double, or a triple bond, and then we can have lone pairs as well. So on our next one here, what if we're going to put our center, there's 1 bonded atom, and then a lone pair. Both of these are examples of steric number 2, or 2 electron domains. Off of the center, there was 2 bonded atoms. Off of the center, there was 1 bonded atom, that's 1 domain, and then there was a lone pair on the center, that'd be the second domain. There can also be lone pairs on the outside atoms, but they don't count as domains. Okay? So, we're gonna fill out number 3 here, steric number 3 or domain 3, and then we're gonna keep going. We'll fill out the other ones during class time. So this one says 3 bonded atoms. So I have my central, there's 3 bonded atoms to the center. Again, these could be single, double, or triple bonds, and then there's 0 lone pairs. Or I could have my bonded atom, 2 bonded atoms, There's my central with 2 bonded. And then I can put a lone pair. That's also 3 domains, or a steric number of 3. And then our last one here is, what if we were bonded just to 1 atom, and then we have 2 lone pairs. Okay, wonderful. Now, electron geometry and molecular shape. Electron geometry considers all of the domains, not just the bonded atoms, where molecular shape only considers the bonded atoms off of the center. That's why it's one big square here, because the electron domains are the same, whether they're bonded atoms or they're lone pairs. So the electron geometry will be the same for both of these, but the molecular shape may or may not be the same for those. Okay. Same here. These are all 3 domains. They all have a steric number of 3. So their electron geometry, the shape around the center that all the domains are making, not just the bonded atoms, that has a certain shape to it. We're going to be using these model kits, and we're going to be making these different shapes and then labeling them and reminding us what those names are. When it, again, like I said, when it comes to molecular shape, then it's only the bonded atoms to the center, not the lone pairs, and so then that name can change a little bit. Okay. Bond angle is the angle between the bonded atoms. Okay, so one more time. Bond angle is the angles between the bonded atoms. Okay. So if I'm going to quickly make that model for this one here. So in order to do that, I have to find a central atom that works for 3 domains. So that means there needs to be 1, 2, 3 ports on here. And I'm going to be doing 3 bonded atoms. 1, 2, 3. Now, imagine with me that I have ones on the outside representing those atoms. The bond angle would be the angle between the bonded atoms. So that would be our bond angle. That's our bond angle. That's our bond angle. And for this one, our bond angle would be 120 degrees. Okay. And then we have 3D shape and hybridization. We're going to save 3D shape. We'll talk about that in class. But hybridization is something new that we haven't spent a lot of time on. Okay? So let's talk through what hybridization is. So will you please turn to page 43. Okay, page 43. And it says, during chemical bonding, different atomic orbitals, S, P, D, undergo hybridization. And I have a really good example for us. So let's draw first the Lewis dot structure for CH4. Okay. I'm going to put carbon in the middle. I start with single bonds to the hydrogens. Okay. And then I see if there's any other electrons. The hydrogens are good, and carbon only has 4 valence electrons, and it's utilizing those 4. 1, 2, 3, 4. So this is my Lewis dot structure. Okay. What we see is carbon has 4 valence electrons, and it's sharing 4 valence electrons. Okay. Now, this is interesting, though, because if we think about a neutral carbon, and I'm going to do an off-bow or an orbital diagram. So this is 1s, this is 2s, and then we have our 2p right here. Okay. Carbon, a neutral carbon atom has 6 electrons. So I'm going to start filling in this orbital diagram. 1, 2, 3, 4, 5, 6. Okay, now, there's a problem because right now it says that these electrons are paired and those electrons are paired, and that these are the only unpaired electrons for carbon. And so based on how this structure is looking, carbon should only be forming 2 bonds, not 4 bonds like we're seeing here. How is it that we could take only 2 unbonded electrons, but it's showing 4 unbonded electrons that then are going to form bonds with the hydrogens? And the way that it works is something called hybridization. Okay? What if this orbital and these orbitals, what if they hybridize? Meaning that they come together. Instead of being separate sublevels, what if they equal out? And their energy will be somewhere in the middle. And instead of having 3 up here and 1 down there, what if we have 4 of them together? Okay, this one used to be the 2s, and these used to be the 2p's, but now they are not distinct s and p's. Instead, we have 4 orbitals, and they are hybrid orbitals, and we'd call that a hybridization of sp. We just brought the s and the p together. And look at this. There was 1, 2, 3, 4 electrons, so let's distribute those 4 electrons. 1, 2, 3, 4. Ooh, now carbon has 4 unbonded electrons, unpaired electrons, that then hydrogen can form bonding orbitals with the hydrogen. They can now share this electron with hydrogen, and hydrogen can share 1 electron, and we can form these bonds. That's what hybridization is. Hybridization is when we have different levels of orbitals, and that they come together, they equal out, and then the electrons are distributed amongst those orbitals. When this occurs, it often allows for more bonding to happen. And it turns out that hybridization is extremely common, and whenever we're forming these bonds, we're almost always doing chemical bonding in hybrid orbitals. Okay, so back to this. And actually, sorry, go to page 41 again. Okay. However many electron domains there are, that's how many hybrid orbitals there are. Okay? So I don't want you to turn back to this page. Stay on page 41. But I just want to show you. This molecule has a steric number of 4, or 4 domains. Our central atom has 1, 2, 3, 4 bonded atoms. Okay? 4 bonded atoms. Off of the center, we have 0 lone pairs. This would equal a steric number of 4. Whatever the steric number is, that's how many hybrid orbitals there are. And we would even clarify on this how many are coming from each. Like s orbitals only have 1, or s sublevels only have 1 orbital, and this is a 2p here, and it has 3 orbitals, and so we clarify this when we do hybridization. We would call this an sp3 hybridization, because the original of these 4 orbitals, 1 was an s and 3 of them used to be a p. Okay? And that would equal, so 1 used to be an s, 3 of them used to be a p, so that gives us 4 hybrid orbitals. And that's what works for a steric number of 4. Okay? All right, so with that in mind, if it's a steric number of 1, that's one of the rare times that we don't see hybridization, that this can be done with just S. Okay, and write this small because we are going to be drawing 3D shapes as well in here. So actually maybe let's put a little like box in the corner here. And that's where we'll be writing down the hybridization. Okay. And then that gives us the remainder of the space to do our 3D shape. All right, so let's do a little box. It's just S. Okay, now look at this one. So we have a steric number of 2. So we are going to need 2 orbitals. One of them used to be an S, and then the second one used to be a P. So we would have a hybridization of sp. Oh, I just wrote it on the wrong one. Oh my goodness, guys. Let's fix that. Here and here. Okay. One more time. Okay, so steric number of 1. Steric number 1, there's no hybridization on this. It was just an s orbital. Okay. Steric number 2, there is hybridization. S is our first one, and then we're also going to need a p, because when we add those together, an orbital from S, an orbital from P, we get 2 hybrid orbitals that addresses the steric number of 2. And then 3. So this one, all the way down in the corner here, this is an sp2, because we need 1 of the hybrid orbitals used to come from S, and then 2 of them came from P for a total of 3 hybrid orbitals. So we'd say the hybridization is sp2, and then the one that we looked at just barely in the example was a steric number of 4, and so this would be sp3. Okay. Something we used to think, this is actually kind of recent chemistry. We used to think that the hybridization for 5 was sp3d, and that makes sense. I'm going to put it in pencil so I can erase it. Because we know after our p orbitals that we have d next. So we used to think that it was sp3d. One of the orbitals used to be an s, 3 of them used to be a p, and 1 of them used to be a d, for a total of 5, steric number of 5. Recently, I'd say the last couple of years, we have done some experimentation that's disproven this. And so it is not hybridization of sp3d, but as often occurs in science, when we go, wait, that's not the case, we're still working on hypotheses and evidence of what is currently going on. So the good news for us in AP Chem is that if it's a steric number of 5 or a steric number of 6, that means no, we're not going to be asked about hybridization. Because we don't currently know what's going on in chemistry at that level. Something's happening, but we're not sure how hybridization is occurring at those levels. Okay, so that's the good news, is once we get into a domain of 5 or 6, then we're no longer going to get questions about hybridization. Okay, wonderful. All right, everyone, this is going to be a more hands-on class, and so I think we're just going to wrap this up right here. We'll do another example of hybridization. We'll be making these different models together and labeling those, and that's what we'll have going on next class. All right. Thank you again for your hard work, and thank you so much for watching these videos and filling out your notes. See you all in class.